All right, this is going to be a wee bit tricky because I am trying to do a screencast on the bus home from the Indian Mountain School, and I'm sure that you can hear the girls on my soccer team in the background. And also understand that the road's bumpy, so my writing is going to be hideous. So here goes. We are going to be talking about two scientists, Mendeleev and Moseley, and what they contributed to this concept called the periodic law. And the periodic law is something that governs how we organize all the chemicals that exist in a way that makes a lot of sense. So, in order to really understand the value of what they did, we sort of have to look at this from a historical context. So, let me just give you a little quick history lesson on what's going on here. And the first thing you should know is that, let's see, in the 1700s, let's say, certainly the concept of elements was known. However, in terms of how many elements were known, that's the difference between then and now. There were very few known elements. And in fact, those that were known tended to be ones that people could easily find. Metals. And they would be metals that were fairly non-reactive, which means that they'd be found pure in nature. And that includes things like gold and silver and copper. Okay, so those are fairly well-known metals. Oh, and certainly, well, I was going to say iron, but frankly, iron reacts with so many things that finding it in its pure form was hard, but heck, I'll put it in there. And also, there were some non-metals. I wasn't sure if I was still recording there. Non-metals. And that included things like oxygen, hydrogen, nitrogen. And then lastly, there was this, those are all obviously gases, but there was also a non-metal that was fairly well known, carbon. So that was the extent of it. About 8 known elements in the late 1700s. All right, so let's scooch to another page. So this brings us to the early 1800s. That was the late 1700s before. So, oops, early. And in the early 1800s, there was a huge discovery. Oh, I got to lock this, hold on. Big discovery, and that was the use of spectroscopy. And what spectroscopy did was, it was the way in which people saw the bright line spectra associated with certain gases and elements. And as a result, and keep in mind, you don't only have to do this by exciting gases in a tube. You could also burn certain chunks of metal, and it would give off a particular spectra, which we all know about. You guys just had a test on that the other day. And but what was most important is that because of spectroscopy, they were able to discover a whole bunch of new elements that they didn't know existed. So as a result of the atomic spectroscopy that was done, then about 60 elements were known. Around this time, there was a scientist whose first name I don't remember, but his last name was Dober Reiner, German dude. Boy, that's not spelled very well. Dobereiner. And Dobereiner was the first one who tried to organize the elements. And in fact, he organized them according to their properties into what he referred to as triads. This is actually kind of a cool concept here. Dobereiner's first triad was lithium, potassium, and sodium. Actually, let me be careful there because, in fact, sodium should be over here, like that, and that shouldn't be, oh, I didn't mean to do that, boo. Select that, that comma right there. And then he had other, so this is one triad. We'll just call this, for now, we'll call that A. He also had a triad B. Sorry, didn't record that. So calcium, strontium, and barium were his next triad. And then chlorine, oh, bad color. Chlorine, I can't remember. Bromine, and iodine. And the way he did this, he arranged these things according to their physical and chemical properties. So lithium, sodium, and potassium were very similar to each other. Calcium, strontium, and barium also. And chlorine, bromine, and iodine were also all very similar in terms of how they reacted with other things as well as their physical properties. The other very important thing that Dobereiner noticed is that if you took some of these properties, these physical properties, or chemical properties, properties in general, associated with, let's say, lithium and potassium, and then averaged them, he would find that they were really close to the properties that one would predict for something in between. In this case, sodium was the one that would be in between. So, for example, let's go over here for a moment. So, let's take a look at an example of this from the group that includes chlorine, bromine, and iodine. So, we know that the atomic mass of bromine is 79.9. Okay? Now, if you take the averages of the masses, the known masses for chlorine, chlorine's atomic mass is 35.5, and then you take iodine's atomic mass, which is 126.9, divide that by 2, in other words, get the average. You would find that actually, I'm going to go up here, that this number is 81.2, which is damn close to 79.9. So the fact that you could almost predict really quite closely the properties associated with the intermediate element led Dobereiner to realize that there was a lot going on here that needed to be sorted out. This brings us to our next fella. Can't remember his first name, but I know it begins with a J. And his name was J. Oh boy, that's messy. Newlands. This is a guy who doesn't get enough credit for what he did. It's kind of sad. And I'll explain to you why that is in just a case. So J. Newlands. J. Newlands was out of England, if I'm not mistaken. But he did his work in the in the 1865. And in 1865, 62 known elements existed. Okay? So about the same as what happened when Dobereiner was doing his work there, a little bit more. And what Newlands did is he organized all these elements, following something similar to what Dobereiner did. And when he organized them all, he noticed that you could actually organize them into groups of 8 repeating elements. So groups of 8. And the pattern repeated itself. So you could have a line of 8 elements, and then just underneath that, another line of 8 elements, and beneath that, another line of 8 elements. And so it was Newlands who was the first one to propose that there was periodicity that was associated with the chemicals. The concept of periodicity. And periodicity simply means that you have a repeating pattern of something. For example, there's periodicity when it comes to the full moon, because the full moon exists or comes around every 27.5 days. Or periodicity with the seasons. In the Northeast, obviously, we see that. And then even periodicity when it comes to music. We have something called octaves. And what's weird about this is that this is the reason why poor Newlands was not taken seriously, because the 8 associated with the octaves of music and the 8 associated with the periodic table that he was developing was so close that everyone sort of laughed at him and thought, how could something as like music be associated with a such an important scientific concept? So he was somewhat ignored, sadly enough. Okay, and this brings us to one of our heroes, Dmitri Mendeleev. Lock this out. And Mendeleev's major contribution was published in 1869. And he was the first to propose a periodic table, which actually looked a heck of a lot like the periodic table that our friend Newlands had created. So it followed his concept, but there was a lot more refinement to his periodic table. Sorry, that's a T. And most importantly, what he was able to do by ordering everything, all the elements according to their atomic mass, was that he was able to predict, based on the pattern that he created, where there were missing elements in the periodic table, which is kind of a cool thing. So, and in fact, as the elements became known, so as elements were discovered, they fit perfectly into what Mendeleev predicted they would be in. So elements were discovered. I'm just going to pause it and write it out. Okay, so the elements that were discovered, they fit into those gaps that were predicted by Mendeleev's periodic table. So that gave him a ton of credibility and gave his discoveries a lot of clout. Hold on, somebody's calling me. So Mendeleev was given hero status, and that brings us a few decades later to a gentleman, Moseley. And what was actually kind of cool about Moseley is that he worked in Rutherford's lab, the same Rutherford that you guys learned about a couple weeks ago. And what Moseley did was I guess you could, sort of a strange term, but he invented the concept of the atomic number. So up until this point, certainly with Mendeleev, atomic masses were known, but the atomic number was something that was completely novel because it was based on the number of protons associated with a particular element. So Moseley was the one who developed this concept of the atomic number. And then he took it a step further because he realized that Mendeleev had done when he did his work in arranging the table, he had made his table based on atomic masses. But Moseley rearranged things. So rearranged Mendeleev's periodic table. But he did that by atomic number instead of atomic mass. Now, there's not a ton of difference between atomic number and atomic mass, But there's enough that when Moseley put this together, it fit even better than what Mendeleev had predicted. Now keep in mind that Mendeleev still had it right. He just, he had the right pattern. He just had the wrong property that he was focusing in on. Instead of focusing in on atomic number, he focused in on atomic mass. So everything fit much better when Moseley used atomic numbers to arrange his table. And that led us to the development of the periodic law. And the periodic law, let me just pause this, write it down, and then I'll let you see it. Okay, there you have it. That's the periodic law. When elements are arranged in order of increasing atomic number, their physical and chemical properties show a periodic pattern. And that is exactly what we're going to be covering over the next couple of days, looking how the modern periodic table helps us to understand the properties associated with each group and family of elements, and how we can predict ways in which elements will connect with each other based on their position on the periodic table. Okay, goodbye.